Assalamualaikum and good day to everyone. Today we will be present our final year project. Our group title is a process simulation of an oxidative torrefaction of biomass and pelletization process. Biomass is known to be the largest renewable energy today as it contributes about 10% of world main supply. Malaysia has an abundance of biomass that is mainly produced from the oil palm plantation. Raw EFB has high moisture level, thus thermal pretreatment of EFB is required before it can be regarded as a good fuel. Oxidative torrefaction is a biomass upgrading process in which biomass is torrefied through an oxygen-containing environment. Many operating parameters influence torrefaction including temperature, residence time, particle size, biomass type, and also moisture content. Pelletization is one of various densification processes that involve compressing biomass into cylindrical hole resulting in pellets. Durability and bulk density of the pellet are the main factor that affecting pelletization. For withstanding transportation, pellets have to be durable and strong. Durability of the pellet can be increased by increasing the moisture content of pelletization. Binders, which are organic or inorganic chemicals, can be introduced to biomass for pelletization in small amount to enhance the mechanical properties of the pellet. Concentration of binder influence the pellet density, mechanical strength, moisture content, and also pellet durability. Mainly, there are 4 applications of the product. The application of biomass pellet fuel not only improves the thermal efficiency of stove but also facilitates storage and operation. It has wide marketing prospect besides stove. The biomass pellet fuels are also applied in home heating system. The stove can work automatically based on the regulated mode and work continuously for a week. Next, the biomass pellet fuel are known to be as a green coal. It is a clean and renewable energy used in industrial boiler. It features long burning time, high combustion temperature, low cost, and also little pollution to the environment. For the problem statement, biomass is known for its irregular shape or fibrous, thus increased difficulty in handling, transporting, and storage. Therefore, pellet is produced. Torrefaction removes a significant amount of biomass initial moisture content. In order to enhance moisture content and pelletizing effect, binder can be used. Binder helps to increase adhesive and cohesive as well as interfacial forces between solid particles. Nowadays, the pellet fuel have been increasing in demand all over the world. Therefore, a large-scale production is needed. In recent years, modeling and optimization of torrefied pellet fuel generation from biomass have attracted interest. Process model simulations such as Aspen Plus useful for understanding the process. Next, there are 2 main objectives of this work. Firstly is to study the oxidative torrefaction of EFB and test the effect of torrefaction at different temperature ranging from 220 degrees Celsius to 300 degrees Celsius with different concentration of oxygen medium, 0 weight percent to 21 weight percent. Next is to study the efficiency of organic binders, lignin, cellulose and glycerol, and inorganic binders, NaOH, CaCO3 and CaOH2 at different concentration ranging from 0 weight percent to 10 weight percent.
Now we move to the overall process. The picture shows the simulation of the EFB torrefaction process plant to produce the solid fuel. This modification process involves the following 3 main assumptions. First is the non-conventional solid with definitive ultimate and proximate analysis. Data was used to using H collision and decollit for coal. The model particle size and distribution was defined using the MCIN CPSD stream class for unconventional and conventional solid, and it assumes that the process is in a steady state. The process starts with the 2 streams will go to the burner, which is the airborne and the net gas, with a fixed flow rate. The Argus reactor was used to burn those components with the air. The design spec function sent to create a flue gas to the dryer portion, and the hot gas was diluted with air before drying to obtain the set point temperature. EFB with high moisture content in the stream W as wood and the hot gas in were mixed before flowing through the dryer. In the input section, a proper dryer dimension, the drying curve factor, and the mass factor transfer coefficient were defined. The raw EFB is fed to the dryer, heating, convection rotary dryer with a moisture level between the 40% to the 50%. As a result, the water in the EFB evaporates and changes to the gas phase. The output gas temperature is the 138.49 degrees Celsius. To produce durable pellets, the wet biomass is dried to a final moisture level of 6%. Then the dried EFB biomass stream that dries wood enter the RG reactor where the unconventional component biomass is converted into conventional component. The compost stream R-Tor-EFB enter the R-Gibbs reactor for the torrefaction. This component will go through the next torrefaction in the R-Gibbs reactor at different temperature between the 200 until the 300 degrees Celsius. In this reactor, the oxide stream containing oxygen will be introduced at different concentration to observe FB condition in oxidative reaction.
For the pelletization process, flash tea separator was used in order to separate the vapor produced from torrefied biomass. The flash tea separator was set at 450 degrees Celsius and 1 bar. Then TOC will enter the cooler and being cooled down to 60 degrees Celsius before entering mill crusher. This mill was used to crush the torrefied biomass before it was mixed with binder. The binders enter the simulation process at binder stream input at the mixer block. The binder was mixed with a ratio of 1 water to 1 binder. The temperature for heater was set at 80 degrees Celsius. Then, in order to produce pellets, the product produced will enter the granulator. After that, the pellet produced will enter the cooler to exchanger. The function of cooler 2 was to cool down the pellet produced. For the performance test, R-Yield reactor and R-Gibbs reactor was used. The SSR was added at the R-Gibbs block.
For the analysis of the product, we found that the message decreased when the oxygen increased. The decrease in message is caused by the degradation of the major biomass component like the hemicellulose, cellulose, and lignin. And then for the energy yield, the highest energy yield at the 5% oxygen concentration. The energy yield was varying at the different concentration and the temperature.
For all type of binder used, the highest density recorded was the pellet without binder. The lowest density recorded was pellet with glycerol at 10%, but has the highest flow rate at 10%. Pellet with calcium carbonate has the lowest volume flow rate at 10%, but highest value of density among all of the binder at 2%. It can be deduced that as the volume flow rate increase, the density of the pellet decrease. This is because high flow rate increases the moisture content of the pellet, hence decreases the value of the density of the pellet mixed with glycerol binder and increases the density of the pellet with calcium carbonate binder. This is owing to the fact that the binder is very soluble in the water, making it simple to absorb the moisture. Based on the result obtained, the HHV value increases when the concentration of the binders increases from 0 to 6 weight%. Then it increases drastically at 8 and 10 weight%. This may be because moisture content increases sharply. The lowest HHV value was at 0 weight% binder concentration and the highest HHV value was at 10 weight%. HHV has a direct relationship with ash content and carbon content. As the concentration of the binder increases, the ash content and carbon content increase in the pellet, thus increasing the HHV value. The cost of the product were estimated as below. The value calculated based on the production. It is calculated with EFB pellet mixed with binder in 10 weight% binder concentration, as most of the parameters shows a positive fuel properties. The price in the industry was 16 ringgit and 50 cents per kilogram.
Now we move for the marketability and the commercialization. The business area in the torrefaction is the torrefaction technology, the sub-desalination torrefaction technology, and selling the torrefaction technology. And then we can use it for the fuel production in region with difficult biomass to mobilize in, and also production of chemical or biomaterials. According to a report by consulting the firm Hawkins Wright, the global demand for torrefied biomass is projected to exceed 70 million metric ton per year by 2025. The past year, the global FBP market has high growth from the 8 million tons per year in 2020 to 30 million tons in 2021. Currently, the European countries are the major consumers of the biomass because they target to the zero emission from the carbon dioxide.
So we move on to the environmental impact. Because wood pellets are a dense energy source and contain little moisture and little ash, pellets burn completely and efficiently. Wood pellet contains very little moisture, so they are able to burn with very little ash. This reduces carbon emission. This makes wood pellets a green and efficient choice. So, material for the pellet is sourced from discarded, untreated wooden shaping pellets. From there, the wood is broken down and then pelletized under high pressure and heat to make the wood pellet fuel. Because the particles are densely packed and contain very little water, it can be easily distributed, hence lower the handling and shipping costs.
This system able to simulate the oxidative torrefaction and the pelletization, and also help to estimate the possible product at each stream. Easy to find the best parameter for the operation of torrefaction at low cost, and the results are close to the actual experiment and precise. For the potential collaborator, we found the two companies that we can collab for this study. First is the Tenaga Nasional Berhad (TNB), and the second is Runhill Utilities Berhad. For the technology transfer potential, we also found the two companies in Malaysia to use our technology. First is the Forest Research Institute Malaysia (FRAME), and the second is Tenaga Nasional Berhad Research (TNB Research).